All right. How is everyone? Good, happy? Online people, good, happy? Great. First assignment has been posted, I think, as most of you know. I've seen already several people have gone in and taken a look. I just wanted to make clear what I think I said in the email as well. Is what I'm planning to do for a lot of these assignments is not make the assignment super long. Wow, that was loud. Let me shut down my email so that never happens again. So my goal is to not make the assignments super long, but there's a whole lot of extra questions at the end of the assignment that are there for practice. If you want practice and you want those questions, they're there. But when you answer any question on the assignment, it'll bring up a little, like on the corner of the question, it should tell you the value, how many points that question's worth. If it says 0 points, that's one of the bonus extra ones. So if you do it or don't do it, it doesn't matter. It won't affect your grade on the assignment. Usually the first, 15 to 25-ish questions, depending on how long the questions are the ones that actually count for the assignment. And then once you start seeing zeros, you'll know that you're in the bonus part. Do it if you like the practice, but don't feel you have to complete that as part of the assignment. I know I've been going through kind of into the future, looking at what these assignments will look like, and they'll change a little bit slightly depending on exactly how quickly we get through the material. But there's one of them has like 80 questions, but only like 20 of them are actually assignment questions, and the rest of them are just extra ones that we have. And I thought, why not put them out there? So we will finish the kinetics chapter today. My plan is to not go any further than kinetics. We'll finish that chapter and then call it a week, and we'll go into the next chapter starting in next week. And so we've done, I'd say, the bulk for sure of this chapter. We talked about how to express rate laws, how to determine rate laws from experimental data, those initial rates tables. We looked at integrated rate laws and how you can figure out the percentage completion of a reaction, essentially, what you're learning there, predicting what the concentration will be after some period of time. We also looked at effect of temperature on reaction rate constants using the Arrhenius equation. So I think that was about where we finished last time. The last thing we're going to be doing in this chapter is quite qualitative, meaning no calculations or math involved. We're going to be looking at energy profiles, sometimes called potential energy profiles or reaction profiles. What these are, basically a picture which shows you graphically what's happening in the reaction in terms of energy. And what we have is basically just like an XY plot where the y-axis here is potential energy, right? Which shows you the total energy of all interacting species in the system here. And this is progress of reaction. So you can kind of think of this maybe as kind of like time, although it's not exactly time. It's sort of like what percent complete is this particular reaction step. And this is showing the adventure of one set of molecules. This isn't showing you, okay, the reaction is 98% yield. If you keep pushing it, it'll go to 99 and et cetera. This is showing you for a single set of reacting molecules or atoms what is going on. So here we have an example where we have reactants, and this line here is the potential energy of those reactants all on their own. Then what's happening here is these reactants come together and they form a high energy state up here, which we call the transition state. Sometimes we also call it the activated complex. So those both mean the same thing. The transition state, we sometimes also give a symbol. The symbol looks like this, kind of like a cross with an extra horizontal line. This symbol is often called the double dagger. That just means transition state. The transition state is basically a high energy state where you have sort of a loose kind of bonding. You know, bonds are like partially formed, partially broken. It's very fleeting. Doesn't have a long lifetime. Like we're talking femtoseconds, very, very short time that the molecules are in that high energy state. And then once they pass through that state, they proceed all the way down to finally give you the products of the reaction, which could be higher in energy or lower in energy than the actual reactants that we started with. So a couple of things to note here. The difference in energy between where you start, which is number 1 here, and the peak of the transition state, number 2, is this activation energy that we talked about in the Arrhenius equation part. The amount of energy you need to put into the reactants to have them overcome, it's like a barrier you need to overcome in order to convert reactants into products. So many reactions are like this, and you think of taking a piece of paper and lighting it on fire. It won't just spontaneously react, even though you have paper and oxygen all surrounding each other all the time. And that's because the transition state, you need to get over that energy barrier. You need to get to that transition state energy by putting energy in. And you can do that with a burning piece of paper with like a match. That's providing the energy to get over the transition state. That particular reaction is very exothermic, and the energy given off by that reaction is enough to be the activation energy for the next molecules down. And that reaction will continue and travel along the length of the piece of paper until the whole paper is consumed. The difference in energy between the reactants and the products we'll be looking at as the change, and this symbol U you may not have seen. You might have seen delta H or maybe delta G, and we'll be putting all those in context in the next 2 units. But yeah, if the energy of the products is lower, we say it's exothermic. If the energy of the products is higher than the reactants, we say it's endothermic. And both types of reactions are definitely possible. There's also another principle that we talk about sometimes in chemistry, which you may have heard or you may not have. It's called the principle of microscopic reversibility. And this principle just states that if you do any reaction in the forward direction, you can, in principle, do the reverse reaction as well, and it'll follow the exact same pathway, just in reverse. So you can kind of think of this as a bit like a roller coaster, and this red line on this graph is like a track. If you put a roller coaster car on the track and go from one side to the other side, you can push it in reverse as well, and it has to follow the exact same track. It can't take a different track back because it's fixed to the track that it's on. The same is true with a chemical reaction. Any one of these energy profiles can be done in the forward or reverse direction, which is why the progressive reaction on the bottom is not really time. Time doesn't go backwards. So if you wanted to do this reaction backwards, then your products really are becoming your reactants, and your reactants are becoming your products. And your activation energy is the energy required to go from here all the way up to here. So there's a much larger activation energy to go in the reverse direction, which is one reason why many reactions only appear to go in one direction, not both directions. Another reason why many reactions do not go in the reverse direction is because if the reaction produces a gas and the gas escapes, then it's not there anymore to do the reaction. So imagine, that burning piece of paper. That paper turns into carbon dioxide and water vapor, which leaves the reaction site. That's not really easily reversible. You can't gather it all back up and put it back in very, very easily. So yeah, EA is the activation energy. It's the barrier that we had talked about. This particular one that we're looking at here would be the energy profile for an elementary reaction or an elementary step. Now remember, an elementary step is the result of a single event, a single collision, or the single breaking of a bond or a molecule or something like that. You can tell if it's an elementary reaction because an elementary reaction will only have a single transition state. Because the transition state you can think about as being like the collision, right? You have 3 molecules or 2 molecules and they collide with each other. At the second that they're most compressed, at their highest energy at that collision, you're at the peak of the transition state. But if you have a complex reaction, complex just means a sequence of more than one elementary step, then what you'll have here is a sequence of these profiles basically just linked together, and there'll be more than one transition state. There'll be one transition state for every step the reaction has in the mechanism. So this example, we have NO2 gas plus F2 goes to 2 NO2F. I think everything here is a gas. I don't know why I left off the gas and the other ones. But if you start here, right at the beginning where the reactants are, there is a first step which goes through this first transition state, which then goes to NO2F plus F plus NO2. So we were at a state there, which is, it looks like products. It's the products of that first step, but then those products then engage in a second reaction, go through a second transition, and then move their way down to products. So there's an EA for the first step, it's an EA for the second step, two different activation energies. Notice that the first one has a much higher activation energy than the second one. A high activation energy, does that translate to a fast or a slow reaction? Yeah, a high EA is a slow reaction. Therefore, the first step is going to be slow. The second one with a small EA is going to be fast. So often what we see is when you have multiple steps, one of those steps is going to be slower than all the others. And you can kind of think of it as being like the bottleneck of the reaction. And often we call this either the rate determining step or the rate limiting step, because that's the step which determines how fast this reaction is going to be able to go. This thing in the middle here, it looks like an energy minimum. It's like it's the bottom of a well, but it's certainly not your final or your starting place. We call this an intermediate state. So intermediate or intermediates would be the compounds present there, are just something that is generated in an early step and then consumed in a later step, right? So it's produced in step one, it's consumed in step two to give you your products. And yeah, we call this part of the reaction an intermediate. Yeah, we've seen this rate determining step. Yeah, this is just a chemistry meme here. Have you read this book, The Little Prince? No? Oh my God. Classic. We did it in high school in French, but we also did it had it around in English too. If you ever read that book, yeah. Never mind. Okay, here's a reaction. Here's the energy profile for a reaction of an alcohol called an E1 reaction, and it's one that we'll study in Organic 1. It starts with this alcohol. It's called tertiary butanol, or I think the IUPAC name is 2-methyl-2-propanol. It'll react with H2SO4 to give you carbon-carbon double bond, which we call an alkene. Plus, it also gives us a molecule of water. And we also get our H2SO4 back. See, it's okay, so this has 3 steps. How do you know we have 3 steps? Because we have a transition state here, transition state here, and a transition state here. The number of transition state is equal to the number of steps. There's 2 intermediates. This is going to be an intermediate here, and this is going to be an intermediate here. The sulfuric acid, which is present at the beginning and present at the end, we would call a catalyst. It's sort of the opposite of an intermediate. Intermediate is generated in an early step and then consumed in a subsequent step, whereas a catalyst is consumed in an early step and then regenerated in a later step. Kind of the reverse. First question, how many elementary steps are in this reaction? Well, count the transition states, count the peaks. We know it's 3. How many intermediates are there? There's 2. There's I1, I2, 2 intermediate states. Identify all the transition states, which we've done. Which one is the rate determining step? So if this is step 1, this is step 2, and this is step 3, which of these 3 steps do you think is the rate determining step? 2, yeah. It's got the biggest EA. The EA here would be basically this height here. This one is just from here to here. And then this one is like super small. Good. In terms of effect on temperature on reaction rates, we know that as you increase the temperature for any reaction, you also increase K, increase the rate constant. And this is how we understand this to be. When you have molecules that are in solution and they're colliding, and if they collide in the correct orientation with enough kinetic energy to get over the EA barrier, right, to create that transition state, then that will allow for a successful reaction. If they collide, they just sort of like drift, and then, if they're moving really slow without a lot of kinetic energy and they collide, that may not have enough energy to get up to the transition state, and therefore may not proceed to product. So that might be sort of a collision that's unproductive, if you know what I mean. So what we're looking at in this case is basically the distribution of kinetic energies of a whole collection of molecules in a container. So if you have a beaker where everything's at, say, 20 degrees versus a second beaker where everything's at 80 degrees, the lower temperature will give you a distribution like this, where most particles will have a kinetic energy of value of that. There'll be a distribution. Some will be lower, some will be higher. A few will be very high, just because for random reasons, maybe 4 molecules slam into it at a right angle and it flies off, because these things are constantly moving and colliding and bouncing around. Some of them are going to be going very fast and they'll have high kinetic energy. If you increase the temperature to a higher temperature, right, like if this was the 20 degrees and this was the 80 degrees, what we see at higher temperature is that it skews more to higher kinetic energies, that more molecules will have a higher speed, higher kinetic energy. There's more energy in the system. And so therefore, it's more likely that when there's a collision, that collision will have enough kinetic energy to get over the activation barrier. So let's say the kinetic energy required to get over the activation barrier is this dotted line right here. Any molecules that have potential energy or kinetic energy that is higher than that value can, through a collision, undergo a reaction. They have enough energy to go over the transition state and give you a product. At the lower temperature, you see the area under the curve for the blue right here. The area under the curve there is sort of the proportion of molecules that have the sufficient kinetic energy to get over the barrier and do the reaction at the low temperature. At the higher temperature, this is everything under red. There's way more, right? Like if you look at the entire T1 curve, the amount, like the area under that curve that's above the activation energy is, I don't know what it is, like maybe 5%, something like that. Whereas under the red curve, the total area under the red curve that's above that energy is more like, I don't know, 30%, something like that. So that means there's far more molecules with enough energy to have a productive collision and give you a product, have the reaction successful. And that's why higher temperatures give higher rates. There's just a higher likelihood that any given collision is going to have enough energy to get over the reaction barrier. That's only one part of it, actually. They have higher kinetic energy. The other one is if they're all moving faster, there's going to be a higher frequency of collisions. So there's more collisions, and each individual collision is more likely to have enough energy to get over the activation barrier. It's kind of two factors which causes higher temperatures to give you higher reaction rates. As we saw, I mean, the Arrhenius equation, we just sort of described mathematically how that looks. We just said increasing the temperature, increase the rates, without really explaining why. This is explaining why, and this is using this, what we call sometimes the kinetic theory. meaning like molecules are, you can kind of think of them as like individual little balls that are flying around. And when they collide, when there's a collision, that's when reactions take place. I just do want to say though, like that model works most of the time. Most chemical reactions are the result of collisions like that. But there are also reactions that are not like that. There can be reactions that happen sort of through space. And these are often reactions like electron transfer reactions, where one molecule donates an electron to something else, but they could be far apart. I mean, far apart. I mean, they can't be a mile apart, but on the scale of molecules, they don't necessarily have to come into contact. But most of the time, yes, the reactions are the result of direct contact, direct collisions. Catalyst are something we haven't really discussed yet. Catalyst is a substance which speeds up a chemical reaction. It's not consumed in the reaction. And the way it speeds up a reaction is by providing an alternative reaction pathway, which has lower activation energy than what would be available to that system if you did not have the catalyst present. So catalysis is an extremely important and extremely economically important area as well. Most reactions that we produce industrially make use of catalysis one way or another. In organic chemistry, it's a very hot topic right now. There are a class of reactions which use palladium actually as a catalyst. Palladium is actually very rare, very expensive, and very difficult to find. And it's necessary because there's very important chemical reactions to make drugs and to make all kinds of things that require this palladium. And there's a researcher at Dow who's trying to make catalysts which work just like those palladium ones, but use nickel instead. And it was interesting. He gave a talk here a few years ago, and he was saying that the big drug companies like Merck Frost and Johnson & Johnson's and Pfizer, these kinds of companies, they'll hire a person whose only job is to play the commodities market to buy palladium. And so they'll buy massive amounts of palladium when its price is low, kind of watch the trends to see when it's high. And like their only job is to procure palladium for that company at as good of a price as possible, because they need so much of it for the catalysis to make the products that they need. Catalysts are also in every single car. Every single car built today has a catalytic converter. And what that does is it catalyzes reactions of byproducts of combustion so that they become something safe on the other side. So if you have carbon monoxide, it'll catalyze the conversion of carbon monoxide to carbon dioxide. If there are unburnt hydrocarbons, catalytic converters will convert those as well into carbon dioxide and water. So using a reaction profile, this is how this would look. A regular uncatalyzed reaction is this black line. This would have, in this example, a single transition state, which you can see is that green TS with the double dagger. The activation energy you could see is right here, right? To get to the top of that black hill. And that would be an example of a reaction with a single step. So it's like an elementary reaction. And the rate of this reaction would be determined by the activation energy of this reaction. And of course, the temperature you're at and so on, concentrations and all those things as well. By adding the catalyst, what you're doing is fundamentally changing the mechanism. You're providing a new pathway. That new pathway is the red pathway. It has two steps, right? You see the TS1, the TS2. It may occur through a completely separate and unrelated pathway to the uncatalyzed reaction. So the rate of the second one is going to be related to the activation energy of the rate determining step, which is going to be this first one, EA, let's call it EA prime. And so because that activation energy is much lower than the original uncatalyzed one, this will be a faster overall reaction. And The catalyst itself is not consumed. The nice thing about that is that the catalyst can then be used again and again and again and again. And you, in principle, only need a very small amount of catalyst to convert a large amount of reactants to products. In principle, what we find is that catalysts eventually slowly degrade throughout a reaction, generally through an unrelated pathway. And that degradation is sometimes called poisoning of the catalyst. And so the catalyst will often lose activity. And so, in the practical world, sometimes catalysts are, not perfect. So they actually measure for catalysts something called a turnover number, TON. So it means if you had like 1 mole of catalyst, how many moles of products could you make from reactants before the catalyst was poisoned and wore out? So, if you had a turnover number of, say, 100, that's pretty good because it means you get 100 moles of product for only 1 mole of your catalyst. And your catalyst would then lose its activity and you'd have to either start again with more catalyst or find a better catalyst, right? You can have turnover numbers of 1,000 to 10,000, 1,000,000. You can have very high turnover numbers, or you can have very low turnover numbers. Like a turnover number of 2 would be really bad because like it's barely even acting as a catalyst then, So depending on your application, that turnover number is an important thing. Also, it means you have to treat your reaction carefully because some catalysts, like those palladium catalysts I was talking about earlier, react with oxygen. So you have to be very careful to keep oxygen out of your system if you're using a catalyst like that, if you want a high turnover number. If you are looking at a reaction that's written as like a balanced equation like this, this is the reaction S2O8 2- plus 2I-, it's a 2-sulfate plus I2. This particular reaction is catalyzed by iron 3+. And so if this is catalyzing this reaction, it has to participate in the mechanism. It has to appear in the mechanism. And if it doesn't appear in the mechanism, it's not really a catalyst. And so this is what the reaction is. Step 1 has iron 3+ reacting with 2I- to go to iron 2+ plus I2. And then S2O8 2-, which is thiosulfate. It reacts with the Fe2+ from the previous step to make the sulfate and regenerates the Fe3+. So the Fe3+, we can identify this as a catalyst in this reaction because it's consumed in an early step and then regenerated in a later step. Okay. Now, this appears, it's like a reactant in the first step and then it goes away. And then in the second step, it comes back. There are other types of catalysis that are maybe not as obvious. For example, a lot of catalysts are just pure metal surfaces, where things will come onto the surface, do a reaction, and then come off. Another example is an enzyme, where an enzyme will bring in a substrate, do some chemistry on it, and then spit out the products. So in that case, those catalysts aren't really chemically transforming into something completely different, right? But they are forming bonds and breaking bonds. There are chemical changes to those catalysts. So yeah, we would identify iron 3+ as a catalyst because it disappears in an early step and then appears later on. Again, unchanged. Enzymes are an extremely important type of catalyst, right? These are the enzymes. Enzymes would be the catalysts that would be present in our bodies, and these catalyze all kinds of reactions in our system. So, in our saliva, there's an enzyme called, what's it called? Amylase, I think it's called. And what that does is it breaks down complex starches to simple sugars. It starts the digestion process. Simple sugars from starches is actually an extremely slow reaction, uncatalyzed. If you put starch, like potato starch, in water and sealed it and left it for weeks, months, years, you'd see no appreciable breakdown into, disaccharides or monosaccharides. The uncatalyzed reaction is extremely slow, but throw in a catalyst like amylase, and there's other enzymes that do this as well, then it becomes quite quick. And I don't know if you ever heard this before, but if you take something like wheat, the actual like little kernels you get off the plant, and you chew it long enough, eventually it starts to taste sweet. And what that is actually is the starches from the wheat release into your mouth, the amylase starts to break them down, and then eventually it's generating sugar in your mouth. So you can start to taste that potentially. So that reaction would happen on the order of minutes, as opposed to the uncatalyzed reaction, which would be on the order of years. So extremely, extremely important. There's a lot of focus on the reactivity of enzymes when you take biochem. Very, very important. And this is like a fancy picture of one. You can see it kind of looks like there's these coils as part of it. Enzymes are basically just proteins, and proteins are long strings of amino acids. And those long strings will fold up in a very specific way when they're generated in the body. And what this is trying to show is the shape of how that kind of all balls up. Okay, so we got catalysis without enzyme, which is the black one, with enzyme, the bottom one. When you have the same type of reaction going on with an enzyme, basically what happens is you have the free enzyme, and then the substrate docks, it comes in, reaction takes place, and the products leave. So the enzyme really isn't chemically changed throughout this process, but you could argue that when these two things come together, there are bonding changes in the enzyme. It's only a small part of the enzyme that actually changes it all, but certainly there is bonding changes that are taking place inside. So you could argue the enzyme is changing and then is regenerated in its free form at the end, just like all the other catalysts that we looked at. Yeah. Here's another example. The elementary steps for the E1 reaction of T-butanol are written below. Step 1, all the molecular species are there. You see sulfuric acid is a reactant in the first step. It basically transfers a proton to the oxygen, so you have OH2 plus HSO4 minus in the first step. This thing that's produced in the first step, that cation, reacts to give you a different cation in water. And then in the last step, that cation reacts with HSO4 minus to give you this new product, which is neutral, and H2SO4. First question is identify any intermediates in this particular reaction. So what are we looking for an intermediate? We're looking for something that's generated in an early step and then consumed in a later step. So I would say, well, this cation is produced in the first step and then it's consumed right away in the second step. So I would call that thing an intermediate. Also, look at this. This one is another cation that's generated in an earlier step, it's step 2, and then consumed in a later step, which is step 3. That's also an intermediate. So, if I was going to identify them, it'd be CH3, 3COH2 plus. C plus, it's another one. HSO4 minus is generated in step 1, and then it's consumed again in step 3. So it's also an intermediate. I think that's it. Identify any catalysts. Well, H2SO4 is present at the start of the reaction. So we only have 2 candidates here for a catalyst, which is the CH3, 3COH, or the H2SO4. But only the H2SO4 is consumed in an early step and then reproduced at the end. That's a catalyst. And that's it. There's nothing else in there that can be a catalyst. So we've identified everything except for a couple of things. The alcohol at the start, we would call this a starting material, or reactant, sometimes we call it. And the water here would be a product, and this would be a product as well. Products are things that you see at the beginning or the end of a balanced equation, overall equation. If you took all these steps and added them together, the catalyst will cancel, the intermediates will cancel, and you're left with a balanced overall reaction. Easy peasy? Not too bad. Good. That's it. So I'm not starting the next unit today, so I'll let you guys go 15 minutes early, whatever it is. But we will be starting the next unit on Monday. And please take a peek at least at the assignment over the weekend. And if you have any questions about it at all, just pop me an email. I'll try to get back to you quickly. And otherwise, yeah, I think we're good. Cool. All right, everyone online, you guys have a great weekend too. Can you show the last slide for a quick sec? Yes. Can you see that now? I'll leave it up for a bit. Great. I wanted to mention too that I have been recording the lectures except for Wednesdays I missed and posting them up there. So they're all on YouTube up until Wednesday's class. So my plan is to re-record what I forgot to record on Wednesday, post that up too. I don't know when I'll get time to do that, but I'll eventually get time to do that. So I'll put that up eventually as well. So there's a complete set of slides. Great. All right, thanks everyone.